I'm currently working on a programming project that is pretty interesting to me but hard to explain, and I decided to make a video showing some core concepts. And yeah, what you can see here is a grid of cores, and each of the 49 cores here is some simulated virtual piece of hardware which is programmable and which can interact with its adjacent neighbors. So in the long run, the interesting part of the project and playing with this program and tool is to make interesting interactions. You can make some kind of really complex cellular automata with this. But let's start simple. We have this grid of cores. The memory is empty currently, so if I hit play now, nothing special will happen. Each core will execute instructions, but 0 word means basically no operation. So you can see the cores working slowly on instructions. Each time this little rectangular thing here jumps to the next word, this means the previous instruction has been executed. But yeah, nothing special happens because these cores are empty with cleared memory and are not yet programmed. But what you can see is that the grid power is slowly going down. So the grid is active, the grid consumes power and uses it to execute no-op instructions. We are going to change that. We want to convert grid power into score, and yeah, this is the first programming challenge. So I have a deck here, and by clicking on it, a new window opens, and I can program a core in assembly language. And if I do that, if I write an instruction here, ISC for increase score, and pass a parameter to it, like the little value of 1, and I hit play now, then something has changed. The 49 cores each execute this first instruction, which tells them to increase the score by 1, and in total this increases the score by 49. Yeah, and then all the no-op instructions follow, and after a while, I fast forward in time here, speed up the process. So yeah, after a while the instruction pointer will wrap around and execute the first instruction again, and you see another 49 points added. And even faster, when all the grid power has been consumed, then we have gained 196 score, which is not really a lot, but it's a start. Yeah, what can we do to increase the amount of final score we achieve? Yeah, the most important thing is to spend more grid power on increasing the score and less grid power on no-op instruction. So we can, for example, change the value of this, the parameter value of this instruction, from 1 to 256, or FF in hex. This is the highest parameter that this instruction will take, and it tells the core to generate not 1 score but 256 score. As you can see, nothing happens. Why is that? Let's speed up again a little, and then you can see how there's a yellow bar growing from left to right. It's a charge bar. The thing is, if you have an expensive instruction, and this instruction is growing more expensive the more score it's asked to generate, then it will have to charge. It will consume grid power, and when it's fully charged, it will execute. So this took a while to charge for each core, but then we got a whooping 12,495 score out of it. So what follows? A lot of wasted energy again on no operation, but then it wraps around, and again the charge bar is filling up slowly, and it's a safe bet. We can say we have a new high score. I have no idea what it will be, but it will be a lot higher than the couple of hundred score we had last try. So yeah, this is an improvement. but it's certainly not the pinnacle of what we can achieve here. So let's try to do better by just repeating this instruction a couple of times, because by repeating it we will not waste any energy on no op instruction. So yeah, this should turn out pretty good. Yeah, that's pretty much the best score we can achieve here, because we converted almost all energy into score. The energy that's still missing here, we shouldn't worry about it too much. So yeah, this problem has a solution now, but it's not the most elegant solution. I mean, we have only 256 words of memory, and you can imagine that in more complex programs it's an important goal to save memory, to write short and very elegant programs. So yeah, to improve this, we can add a new instruction, the next instruction, which if executed will move the instruction pointer to some other place. Yeah, and what I say here is increase the score by a certain value, then go to word 0, which moves the instruction pointer back to the first word, and it will generate more score. Oh, okay, this is a little problem. All the cores are almost charged up, but we've run out of grid power before they could contribute the last batch of points to our total score. So 37,000, that's not as much as we had before. So this optimization is actually a large step back in efficiency. Yeah, by adapting the parameter, we should be able to fix this. Yeah, okay. This is a pretty acceptable result for such a simple scenario, and I think I will make more videos and show you how to write more complex programs to solve more complex puzzles. But yeah, this is the beginning, and the basic concepts of CoreSociety should be clear now.